Hey everybody, welcome back to chemistry, and we're continuing on looking at the relationships between masses and moles and atoms and molecules. So at first we were looking at that in the context of elements, but now we're going to be looking at it in terms of compounds. So one thing I want you to sort of remind you of is that what I have here is a periodic table. And what you can do is you can look underneath any of these elemental symbols and see a number there. And that number is the average atomic mass. And units for the average atomic mass are in AMUs. Now you might remember you can look at that number and know that that number is exactly equal to the mass in grams of that element when you have 1 mole of that element. So we're going to expand a little bit here because the problem is this. As you know, there are a lot of interesting molecules that are not in the form of elements. They could be, for example, 2 atoms of the element stuck together is a possibility, or it could be just different elements stuck together to form compounds. So what do we do about the molecular mass of those kinds of things? Well, it's actually pretty simple. So just to kind of focus our attention, let's think about oxygen. If you have 1 oxygen atom, its atomic mass in average atomic mass units is 16.00. So that indicates that if you have something with only single oxygen atoms, 1 mole of that something will have a mass of 16 grams. But as you know, oxygen, for example, in the air is not in the form of individual oxygen atoms. Instead, it's really in the form of 2 oxygen atoms stuck together. So the question is this: what do you do about that? What happens when you are trying to figure out the molecular mass, not of, say, an element that's made of single atoms, but an element like oxygen, which is made of 2 atoms together? And it's actually a pretty easy problem to solve. So you might remember that the mass of a single oxygen atom in atomic mass units is 16.00. So if you have O2, the molecular mass of that molecule in atomic mass units is going to be double that. So it's just going to be 16 plus 16, so it's going to be 32 AMUs. And so I sort of have a picture there of oxygen, and you can see that the molecular mass of O2 stuck together is just double its atomic mass of 16, so it should be 32. Now how about something like sulfur? Well, the individual atomic mass of sulfur is 32.07, but in sulfur molecules, you have 8 of those atoms stuck together. So you might expect the molecular mass to be 8 times that number, and it is. So if you take 32.07 times 8, that will be 256.56 AMUs. And so the molecular mass of S8 there is going to be that number, 256.56 AMUs. So one of the things we now want to look at is we want to look more broadly at molecules. So as you know, most molecules are made of different elements stuck together. And you don't necessarily have 1 of each element stuck together like sodium chloride. Now, molecules can get pretty complex. And so you might have 2 atoms of 1 element stuck to 3 atoms of another element, for example. And so what you want to do is you want to try to find a molecular mass of these complex compounds. And so what we're going to do is we're going to do that. I'm going to show you how to do that. And if we do find the molecular mass of a molecule and it has covalent bonds, it is called a molecular mass. However, it has a different name if it is instead not a molecule but an ionic compound. If it's an ionic compound, it's called a formula mass, but it's basically found in the same way. So let me give you an example. Let's say we want to figure out what the molecular mass of chloroform in AMU is. And so the formula for chloroform is 1 carbon bound to 1 hydrogen with 3 chlorines attached. So it's not too difficult to do. All you have to do is for each element look up the atomic mass or the average atomic mass of that element in the periodic table, and you multiply it by the number of atoms that molecule has for each of the elements, and you should get a mass that can be accorded to that element. So for example, when you have CHCl3, chloroform, you have 1 carbon atom and it has an average atomic mass, or if you want to call it an atomic mass, of 12.01. So the total mass contributed by carbon is 12.01. With hydrogen there, you only have 1 of them, and its atomic mass is 1.008 as indicated in the periodic table, and so the mass accorded to hydrogen is that. Now there are 3 chlorines there, so if you want to find the total mass attributed to the chlorine, you take the 3 chlorine atoms and multiply it by the average atomic mass of chlorine, which is 35.45, and you get that number there. So 106.35 is the mass accorded to chlorine. So what you can see is that of the total mass, which is 119.37, most of it is from chlorine because chlorine atoms are relatively heavy, and on top of that, there are 3 of them in each individual molecule. So this is the molecular mass of chloroform, and again, this is a number in atomic mass units. You can do the same thing for ionic compounds. Now it's just called a formula mass. So just to kind of remind you what that is all about, let's say you had sodium chloride, and as you know, 1 sodium atom binds to 1 chlorine atom. And so what you can do is you can calculate a formula mass for sodium chloride pretty easily. You just add up the average atomic mass of sodium, which is 22.99, plus the average atomic mass of chlorine, which is 35.45. And you get that value, 58.44. Now, something to keep in mind is that when you have that formula mass for sodium chloride, that is due to 1 formula unit comprised of 1 sodium ion in purple and 1 chlorine ion in green. Now, a sodium chloride crystal is just going to be that formula unit that's just sort of spread out in all 3 dimensions. And so the formula mass is sort of the simplest ratio of masses of sodium chloride you can possibly get. So just keep that in mind when you're dealing with formula masses, is that, again, you're really only looking at the simplest whole number ratio of the different elements there. So let's figure out what the formula mass there of this ionic compound is, which is aluminum sulfate. And this is a little bit trickier. So here the problem is the formula is a little odd. So you have aluminum sulfate, and so it's Al2, and then in parentheses SO4, and then that's taken 3 times. So let's carefully count the number of atoms there first. So after you do that, what you'll notice, that compound has 2 aluminum atoms, and then there's 1 sulfur within the parentheses taken 3 times. So there's a total of 3 sulfur atoms in the formula unit. And then you have 4 oxygen atoms within the parentheses taken 3 times. So there's a total of 12 oxygen atoms in the formula unit. So let's say you want to work out the formula mass of that Al2S3O12. You pretty much do it in the same way. So if you have 2 aluminum atoms, each one has the average atomic mass of 26.98, and you can work out the mass that is contributed by aluminum. Same thing with sulfur, there's 3 of them there. And then oxygen, there are actually 12 of them. And then each of the oxygen masses is 16. And so you can get a total mass of 342.14. And again, that mass will be in AMUs. Okay, so here's where it's getting kind of important. What is the molar mass for molecules or formula units? It's defined this way. 1 mole of either molecules or formula units is equal to x.xxx grams of molecules or formula units, where x.xxx is the molar mass of molecules and formula units in AMU. So for example, we know at this point that a single oxygen molecule, which is O2, we know its total molecular mass is 32.00 AMU. What that basically says then, that the molar mass of oxygen, because again, its molecular mass is 32.00 AMU, that would indicate that there is 1 mole of oxygen will contain 32.00 grams. How about chloroform? Well, we just calculated that the molecular mass of chloroform is going to be 119.37 AMUs. And that number, again, is the mass of chloroform in 1 mole of chloroform. How about aluminum sulfate? Again, previously we just calculated the formula mass of aluminum sulfate to be 342.14 AMU. And so it's that number, 342.14 in grams, that will be in 1 mole of aluminum sulfate. So these gram masses that you find in 1 mole of these molecules or formula units are called molar masses. And so we can use this information to solve problems. And so that's what we're going to do next. So let's go ahead and do problem number 1, which is how many moles are there in 34.2 grams of magnesium chloride? So what I want to do is I have indicated the formula mass of magnesium chloride there is 95.21 AMU, but let's go ahead and just confirm that. Let me show you how I work that out. So the problem is here, we have 34.2 grams of magnesium chloride. And what we're trying to find is how many moles of magnesium chloride that is. So you need to find a relationship between grams of magnesium chloride and moles of magnesium chloride. So here you really need to know what the formula mass of magnesium chloride is, because it's that number of grams that is found in 1 mole of magnesium chloride. So I've actually listed there as 95.21, but let me show you how I get that. You have to go to the periodic table and add up the average atomic masses of the elements in that molecule, and with as many atoms of each element as there is. So if you're trying to find the formula mass of magnesium chloride, this is what you do. You take the average atomic mass of magnesium, and it's 24.305 AMU, and then you add to it that of chlorine taken twice, right? Because the formula of magnesium chloride is MgCl2, so we need 2 chlorine masses. So it's going to be times 2, let's see, and that is 35.45 AMU. So what you should be able to do is add 24.305 from magnesium and then 2 times 35.45 from chlorine, and then what you should get to correct number of significant figures for the formula mass of magnesium chloride is 95.21 AMU. Now, what that tells us is it tells us the molar mass of magnesium chloride. If the formula mass of magnesium chloride is 95.21 AMU, that means there are going to be 95.21 grams of magnesium chloride in 1 mole of magnesium chloride. So we can use that molar mass to solve the problem. So it's going to be times 1 mole magnesium chloride over 95.21 grams of magnesium chloride. So grams magnesium chloride should cancel. You should get an answer moles magnesium chloride. So it's 34.2 times 1 divided by 95.21. It should give you your answer of 0.359 moles of magnesium chloride. Okay, so let's move on to the next one. Okay, problem 2. How many grams are there in 8.9 times 10 to the 24 iron chloride formula units? Okay, so we have 8.9 times 10 to the 24 iron chloride formula units. I'll write form U here. And so what we're trying to do is we're trying to get that into grams. So let me write that down here. I think we may need some room for this. So it's going to be some answer in grams of iron chloride. Okay, so let's think about how we're going to approach this problem. So I cannot think of a way to directly convert the formula units of iron chloride into the grams of iron chloride. But what I do remember is that 1 mole of anything is 6.022 times 10 to the 23 of that anything. So if you have 1 mole of formula units of iron chloride, you will have 6.022 times 10 to the 23 formula units of iron chloride. So you can use that relationship to get formula units of iron chloride to moles of iron chloride. And then once you have moles of iron chloride, you can use the formula mass of iron chloride, which we'll have to work out to convert that to grams of iron chloride. So let's go ahead and do that. So remember, if you have 1 mole of formula units of iron chloride, that's going to be equal to 6.022 times 10 to the 23 formula units of iron chloride. So we can use that equality to set up a fraction that would be useful. So let's get formula units into moles. And so what I would do is times 1 mole of iron chloride over 6.022 times 10 to 23 formula units of iron chloride. And so let's see where we're at now. So it looks like iron chloride formula units cancels, and so right now we're at moles of iron chloride. And so now what we want to do is convert moles of iron chloride to grams of iron chloride. So you're going to have to work out the molar mass of iron chloride. So let's remind ourselves how we do that. We have to add up the average atomic masses of iron and then chlorine 3 times. Okay, so iron is 55, so let me write this down. Formula mass of iron chloride is going to be 55.845 in atomic mass units plus 3 times 35.45. And so let's work this out. So it's 35.45 times 3 okay, and so I get a formula mass for iron chloride of 162 on my calculator 195. Let me take a quick look at this, and it looks like this is going to be rounded to 162.20 atomic mass units. Okay. Now, if that's the formula mass for iron chloride in atomic mass units, then that number again is the number of grams of iron chloride in 1 mole of iron chloride. So what we can go ahead and do here is move this problem. We're going to continue it down here, and then we're going to multiply this by 162.20 gram of iron chloride over 1 mole of iron chloride. And so let's see where we're at. Moles iron chloride cancel, and we should get an answer in grams. Okay, so the math should be 8.9 times 10 to the 24 times 1 times 162.20 divided by 6.022 times 10 to the 23 divided by 1. So worked out to correct number of significant figures, the answer should be 2.4 times 10 to the 3 grams of iron chloride. Okay, so let's do one more. It's a little trickier. Okay. So what volume of ethanol in liters is occupied by 5.0 times 10 to the 23 molecules of ethanol? Okay, yeah. Okay, so we have 5.0 times 10 to the 23 molecules of ethanol. I'm going to abbreviate this ETOH for ethanol. And so eventually we want to get this into liters of ethanol. So that may be a little tricky. Okay, so let me think about how I might approach this problem. So remember I was telling you way back whenever you have atoms or something or molecules of something, which is something times 10 to the 23, you're near that. Atoms or molecules, I would just convert it to moles first. So we're going to get this to moles. Now, what we can do is we know the molar mass of ethanol. So if we know the moles of ethanol, we can get the grams of ethanol. So how can we get grams of ethanol to liters of ethanol? Well, ethanol is a liquid, and so it has a particular density. So we're told actually in that problem the number of grams of ethanol in 1 milliliter of ethanol. So we can get grams of ethanol here to milliliters of ethanol, and then convert milliliters of ethanol to liters of ethanol. So it's really not too difficult of a problem. So let me write out the fractions. So it's going to be times 1 mole of ethanol over 6.022 times 10 to the 23 molecules of ethanol. Molecules of ethanol cancel, you get an answer in moles. Let me continue the problem down here. So we need to get moles of ethanol to grams of ethanol. You need to know the molar mass of ethanol. So you could, if given a formula, work out what the molar mass of ethanol is. But fortunately, we're given that. So it's 46.07 grams per mole. So it's times 46.07 grams of ethanol in 1 mole of ethanol. Okay. And so now we need to get grams of ethanol to milliliters of ethanol. So we need to know the density of ethanol. So we're given that. So it's 0.78 grams per milliliter. So what I'm going to do is I'm going to put 1 milliliter here and then 0.78 grams of ethanol down here. So grams of ethanol cancels now. And so now we have to get milliliters to liters, and that's not too bad. So I remember that there are 1,000 milliliters in a liter, so I'm going to write this out like that. And so if you were to take 5 times 10 to the 23 times 1 times 46.07 times 1 times 1, divide by 6.022 times 10 to the 23, divide by 1, divide by 0.78, divide by 1,000, you should come up with, to correct significant figures, 4.9 times 10 to the negative 2 liters of ethanol. All right, thank you for listening. We'll see you next time.